Okay, our last speaker today is Alexander Smith, who will speak on 2 to the k-Selmer groups and Goldfeld's conjecture.
Great. Thank you, Bjorn, for the introduction, and thanks to all the organizers for the invitation. I'm very, very happy to be here. So Jordan mentioned in his talk that there's this sort of philosophy that a variety in general shouldn't have rational points unless it has a good reason for having rational points. And the standard example of this, I would say, is Falting's theorem. So genus at least 2, we know finitely many points. But the situation is also very interesting for genus 1 curves, for elliptic curves. And so the starting conjecture here is Goldfeld's conjecture, which I'm just going to state over Q. Sorry, let me go a little bigger. So take E to be the elliptic curve y squared equals x cubed plus ax plus b, defined over Q. And we're going to take the notation of E with the superscript d, and this will denote a quadratic twist of E. So ED will be the elliptic curve dy squared equals x cubed plus ax plus b. And so for d any rational number, this is going to be another elliptic curve that's geometrically the same as our original one, but which is different number theoretic properties because it's a different elliptic curve over Q. Then what Goldfeld's conjecture claims is as we take a look at more and more twists, so say as n goes to infinity, if we look at the set of twists such that, well, first d has magnitude bounded by n, and the rank of E twisted by d is equal to r. So r here is some non-negative integer. So out of the set of all twists, this size, the size of this proportion should be 1/2 if r is equal to 0, 1/2 if r is equal to 1, and 0 otherwise. Oh, so let me write that as. Okay, and so in light of the philosophy, what this is saying is that an elliptic curve, or a twist of an elliptic curve, has a good reason for having either rank 0 or rank 1, but there aren't really very often good reasons for higher rank than that. Now, when this conjecture first came out in 1979, it was not universally accepted as being true, since most experimental evidence suggested that rank 2 curves happen more often than 0% of the time. But the heuristics changed in the late 90s, and recently Park, Poonen, Matchett-Wood, and Voigt came up with a heuristic that contains Goldfeld's conjecture and also makes some very strong predictions about what happens in higher rank cases and how often all the various ranks happen. But we're going to focus on just this version of the statistical question for this talk. And so I want to mention why rank 1 is expected to happen. And to do this, I'm going to go with my favorite curve ever, which is the congruent number curve. So the congruent number curve is just the elliptic curve y squared equals x cubed minus x. And we're interested in its quadratic twists. So this is an elliptic curve with J invariant 1728. So that means that you could have sextic twists of this if you wanted. Or sorry, no, quartic twists. But it's also a very important elliptic curve because it almost motivates the entire study of elliptic curves. If you look at Andrew Wiles's synopsis of the BSD conjecture for the Clay Math Institute, it'll mention this curve. and its properties. And that's because if this elliptic curve has positive rank, then D is what is called a congruent number. It's expressible as the area of a right triangle, all of whose side lengths are rational. And in that form, these things have been studied for something like 800 years. They were studied by Fibonacci, they were studied by Fermat, et cetera, et cetera, et cetera. And the interesting divide here is between when D is equal to 1, 2, or 3 mod 8, and when D is equal to 5, 6, or 7 mod 8. So these are our two cases. Yeah. And the reason these twist families are expected to behave very differently is because of the L function associated to them. And specifically, it looks like I'm going to put the heading on the right. We can calculate the global root number. And for twists in this family, the global root number is equal to +1. And in this family, it's equal to -1. So the global root number is the sign of the functional equation. You have a relation between your normalized L function and the normalized L function of 1 minus s, and it can either be they're equal or they're the opposite of each other. And that's what this describes. The global root number is interesting because it's a product of local symbols, but in addition to that, it also gives us what the analytic rank should be. So the vanishing of the L, order of vanishing of the L function. So for D equal to 1, 2, or 3 mod 8, we see even analytic rank. And on the other side, we see odd analytic rank. And the importance of this, of course, is the BSD conjecture. And so what BSD tells us is that in this column, where the analytic rank is odd, that should mean that the actual rank of the elliptic curves are odd. So these should all be congruent numbers. So rank 1, 3, 5, 7, all of these correspond to twists of positive rank, and so these are all congruent numbers. Meanwhile, because on the left-hand side we could have rank 0, 2, 4, 6, whatever, we don't actually have a prediction for how the ranks should be, or BSD doesn't tell us whether these should be congruent or not. But then we have Goldfeld's conjecture. So the reason we expect this to be 1/2 and not 0, the reason that there are some curves with positive rank is because of BSD. Because of these sign forcing things, what Goldfeld should tell us is 100% of D equal to 1, 2, 3 mod 8 are not congruent. So 100% of these twists have rank 0. And on the right-hand side, 100% have rank 1. OK, so that would be a good goal. It would be really, really nice to prove this. But this is hard, or it's harder than something I can handle, because if you want to prove something has rank exactly 1, and you don't want to use the Burchard-Swinnerton-Dyer conjecture, you're going to have to use something like Gross-Zagier. And I am not very good at this. So let's make a slightly weaker goal for ourselves. Instead of proving 100% rank 1, let's just aim for 100% of rank at most 1. And then on the left-hand side, we have 100% rank 0. So this is the goal, or this was the ultimate goal of my project. And so the question is, how do we prove something has an upper bound in rank? And the answer every single time is you're going to have to use a Selmer group. So that'll be the first section here. Okay. So given an exact sequence, or for any positive integer, we have an exact sequence which takes the n torsion of an elliptic curve into the whole elliptic curve. And then this is obviously the kernel of the multiplication by n map. Okay, so this is just a map between algebraic varieties, or as I like to think about it, it's a map between Galois modules. And the reason I like to think about it in terms of Galois modules is because the next step to define the Selmer group is to take the associated long exact sequence. And you can go through the whole thing, and what you get is that this turns into, by the long exact sequence, first we have the q points of E, mod n times themselves. We've already seen this group once today in Jordan's talk. And this maps into the first cohomology group of the n torsion of E. And then this maps into H1GQE. And so we have at least this portion of an exact sequence. And that's great, because this tells us everything we could possibly want about rank. And this, at least, is a elementary object. The issue, well, there's two issues. The first is that this is an infinite group, as it stands. So it's not going to tell us anything non-trivial about rank unless we incorporate something about this. But when we do that, we realize that proving something is in the kernel of this map is really, really, really hard. So that's also a no-go. But the one thing we can do is we can consider local behavior everywhere. So we can't prove that a cocycle here vanishes in here, but we can at least check that under the restriction map to any of the associated places, we have vanishing. So let's call this map phi. And so I'm going to put the definition here. So the definition here is that we can then say that the n-Selmer group of E over Q is going to equal the kernel of phi. And this is a sort of concrete object, because this is a concrete object, and figuring out if these local conditions are satisfied is also a concrete condition. But at the same time, it contains a copy of EQ over NEQ, which means it can tell us information about rank. And specifically, let me define the n-Selmer rank of our elliptic curve to equal the max k, so that z over nz to the k injects in some way into the n-Selmer group of E. And now, because I don't want to deal with torsion, I'm going to get rid of it. So the image of the Q torsion of E. Okay, and so the important thing about this is that this is always going to be an upper bound on rank. So if we can find a situation in which, so what we really want to do is we want to be able to control the statistics of all of these Rn. If we could do that, that would be super overkill for proving this. Unfortunately, almost every single case of Rn looks like it's completely hopeless. Maybe R3, I guess, but even that, the information will be very, very partial.
Can I ask a question?
Yes.
So you're mounting up only the image of the n torsion, but it could be the other torsion could
Oh, I
make it
suppose.
smaller.
So
Do
you're
you
thinking
wanna
like
take
n to
all?
the k or something?
Yeah.
Yeah,
So
let me
for
do
example, you wanna
that.
just take all the torsion then?
Well, we've got an elliptic curve over Q, so let's be a little bit saucy about this. Can I do 24? Yeah, I'm going to put a 24 there, I think. Is that good? No, shoot, 7. Big number. EQ tor. There we go.
Okay.
No, that's okay. Okay. So yeah, I'll write this as facts. So the first fact is actually conjecture. So I hope that's okay. And the conjecture is that eventually, if we take a larger and larger n, Rn of E should equal the rank of E. So if we're able to control enough Selmer ranks, we should be good. Now, it turns out that the one case where we can control Selmer ranks is the one in the title of the talk, which is the 2 to the k-Selmer ranks. That is where all of the progress has really been made, starting with R2 by Heath Brown and others, and then continued by me for the other things in the tower. So the second fact is that if we take a look at the 2 Selmer rank, it's an upper bound for the 4 Selmer rank, which is an upper bound for the 8 Selmer rank, ... And all of these are upper bounds for the actual rank. And of course, if this conjecture holds, eventually this will stabilize at the actual rank. And the final thing I want to mention about this sequence right off the bat is it agrees with the parity, well, for the congruent number curve given by this table, but in general, we have that R2, R4 have the parity of the analytic rank. Okay, so what we want to do is we want to control how this sequence behaves. We want to figure out what the distribution of the sequence. And because of this last thing, or this last fact, we know that the transition probabilities from one element in this sequence to the next are going to be such that odd states map to odd states, and even states map to even states. There's a couple different possible explanations for that, but the one that turns out to be correct comes from the theory of alternating matrices. So any sort of alternating matrix is going to have even rank. And so that means that if we go from an alternating matrix, the number of rows it has, to the size of its kernel, we're going to maintain parity. So let me take a definition. For n greater than or equal to j, take p alt of j given n to be the probability in n by n alternating matrix over F2 has kernel dimension j. Okay. Great. So now that I have that on the board, I can state the theorem. So if E over Q obeys certain technical conditions relating to the Galois action on 4 torsion, then given R2 greater than or equal to R4, etc., up through R2 to the k of the same parity, if we take a look at the set of twists such that R2 of ED is equal to R2 all the way up to R2 to the k ED is equal to R2 to the k. And we compare it to the larger set, which follows the same exact sequence, but only up to 2 to the k minus 1. So obviously this set will always contain this, and the size of this set in this is going to be given by the chance that a randomly chosen alternating matrix with r2 to the k minus 1 rows has kernel of dimension r2 to the k. And so to finish this theorem statement, I definitely need to explain what technical conditions we can allow. E obeys the technical conditions. And here, things get a little bit case-wise. So if the first case is that if we take a look at the Q rational points, and specifically the two torsion points, this is of maximal size. So in this case, the rational part of two torsion is all of it. And in addition to this, if this is satisfied, what we need is that E has no rational cyclic isogeny. Oh, sorry, rational cyclic isogeny of degree 4. And an alternative way to state this condition, by the way, is there's no point of two torsion, such that if we mod out this elliptic curve by that point, we take that isogeny, that resulting elliptic curve has full two torsion. If there is such a point, then you can always use it to make an isogeny. And that actually turns out to be what the trouble is that there's this companion curve if this condition isn't satisfied, which looks too much like E. And this really comes to a head when we take a look at partial two torsion. So if the rational points contain just one extra point E, then the condition we need for this is that if we take a look at the field generated by the two rational points of E, this is always going to be a quadratic field. And what we need for the technical condition to be satisfied is that this field does not equal the field of E divided by E two torsion. OK, so these are the first two cases. This first case was the first one that I figured out back in 2017. And it includes the congruent number curve as a huge example. The second case is more recent work, as is the third case, which is actually the simplest to state, which is the technical conditions are just satisfied with no extra requirements if there is no two torsion. So that's nice. But yeah. The really interesting case here is number 2, for reasons that I will describe. OK, so now, thanks to this theorem, we have sort of transition probabilities between, say, the 2-Selmer rank and the 4-Selmer rank, 4-Selmer rank and 8-Selmer rank. And in fact, this looks like a Markov chain, where only the most recent state matters for determining what the next state is. And so in order to fully describe this Markov chain, all we need to do now is come up with the initial probabilities. In case 1, this was done by Kane, following work of Heath Brown. But then 2 and 3 are results of mine. Actually, maybe result 2 is also a work of Kane and Klagsbrun and others. Yep. So. All right. So here's the base case theorem. In cases 1 and 3 above, so if E either has full 2 torsion and no rational cyclic for isogeny, or if its 2 torsion is trivial, we have that as we take a look at more and more twists, so limit as n goes to infinity as before, and we divide the number of twists up to n such that R2 of ED is equal to just R2 divided by 2n. This is equal to, let me write something down and then I'll explain it. 1/2 times the limit as n goes to infinity as P alt of R2 given 2n plus R2. Okay, so this is a little weird as I've written it here. What this is saying is it's saying that the 2-Selmer rank should behave like the kernel size of a randomly chosen alternating matrix over F2. But this runs into the problem of if that matrix has an even number of rows, the kernel size is always even, and if it has an odd number of rows, it's always odd. So in order to normalize for that, we have to put this 1/2 here, and then correct for parity. But then once we do that, the limiting process works great. And this agrees exactly with what's predicted by the heuristics of Bargava, Kane, Lenstra, Poon, and Rains, as does this theorem here. And so, as I said, this works for full 2 torsion and no 2 torsion at all. And then there's one more weird case, which is when we have partial 2 torsion. And what happens in that case is, well, let me write it down as well. In case 2, this works, as in we get the same statistic, if we replace R2 of E twisted by D by the minimum of R2 E twisted by D and R2 of the isogenous curve still twisted by D. Okay. Yes?
The first thing that you gave, what prevents the between 0?
In this one. This is why I was careful about this descending sequence, I hope. If all of those are, if we have a non-decreasing, or sorry, a non-increasing sequence, R2 through R2 to the k, and the parities are all the same, and they're all greater than or equal to 0, so long as we choose n big enough. So I guess I should have put in n greater than 1 at some point. But as soon as we get to a big enough n, there's always going to be something in the denominator, which is a combination of the previous parts of this and this. Great. So let me explain for a second what goes wrong in case 2. What happens is, because of this weird isogeny, you get isogeny Selmer groups. And normal Selmer groups are self-dual, or the way they're constructed is you intersect 2 isotropic subspaces. But if you have an isogeny like this, it throws off like the size of the subspaces. Okay, so that was a horrible explanation of what's going on, but let's roll with it. The point is, usually one of these is very, very large, as in it doesn't have a real distribution at all. It grows with the number of or the number of prime divisors of D. And this is actually good. This is why we had to assume this condition, is because we like this behavior. Because if one of these gets really big, then the other Selmer group behaves well enough for us to play this game with it. So yeah, this partial case is, there's some interesting structure going on in it. But in any case, we now have the initial states for our Markov process. And so we can draw the Markov process. I'll just draw the last few states of it. So 0 maps to itself 100% of the time. 1 also maps to itself 100% of the time. 2, there's 2 things that can happen. Half the time it goes to 0. And half the time it goes to itself. There's only one non-trivial alternating matrix over F2 with 2 rows. 3 has a 1/8 chance of going to itself and a 7/8 chance of going to 0. And then 4 has a 1 in 64 chance of staying at itself, a 28/64 chance of going to 2. Sorry, I never ever get that number right. Oh, it is right. Cool. And a 35/64 chance of getting to 0. And we can continue this forever. But the cool thing about this is we have this column and this column. And half the time we start out on the even side, and half the time we start out on the odd side. So if we just run this Markov process forever, 100% of the mass is going to end up in one of the 2 final states. And so as a corollary of this, we get what I stated as our goal before. So for E satisfying the technical conditions, if we take a look at the set of twists such that the to infinity Selmer rank of E twisted by D is equal to R, and we divide that by the number of twists. This is equal to a 1/2 if R is equal to 0, 1/2 if R is equal to 1, and 0 for R greater than or equal to 2. Okay, and so because R to infinity is an upper bound for rank, this precisely gives us our goal. We know that 50% of the time the rank is 0, and 50% of the time the rank is less than or equal to 1, and strongly hinted to be 1 because of the Burton-Swinnerton-Dyer conjecture. So another way to phrase this, or something that follows from it, is for these elliptic curve families, BSD implies Goldfeld's conjecture, as does the parity conjecture and several different kinds of p-converse statements you can make. Yeah. Okay. So now that I've got into sort of the main result for elliptic curves, I want to give a few ways that we can generalize this whole picture. Because there's many, many natural things we can do that still seem like they should work for us. Oops, come on. While I'm erasing, any questions so far? Yes?
So you're summing over all digits as opposed to integers? Does it make a difference when you just sum over square root integers?
All of the what?
Can you just restrict to square root integers?
Yes. So
Can you repeat the question?
yeah, the question was, so far I've only looked at all integers. What about the square-free integers? And these two sorts of questions are completely equivalent. If we can prove a density result for the square-free integers, we can prove it for all integers and vice versa, because if we twist by something that's not square-free, the square-full part just falls out.
You're repeating the Turing twist more frequently than a non-Turing twist in sequence. So you can get a weight of 1 over a weight of 2, something like this.
Yeah, so that is true. What happens, though, is the weights that you get so one thing I will say is all of the convergences in my proof are very, very slow. So like as if for the twists up to n, the saving term is about log n. And so compared to that, you don't need to consider squareful parts that are very large. Like you just need a square. You can need to consider something like squareful parts up to log n squared or something like that. Sorry, I'm sort of messing up the translation from one to the other, but I'm pretty sure it's there. Yeah. Anyhow, all of my methods, yeah, they work for square-free integers. And I just state these theorems for all integers because it's easier to write down. Okay. So I'm going to give a bunch of generalizations and a bunch of problems with those generalizations that we need to deal with in order to actually generalize. So the first generalization is go from Q to a number field F. Okay, so the first problem here is the question of ordering. Like obviously we just had a discussion about ordering in Q, which for this I weight the small numbers too much because I'm not considering square-free numbers. But those problems get much worse in number fields, and the notion of natural density, which is based on the ordering of the norm of your twist, is, in my view, somewhat unnatural. So there's a question there of what ordering you can choose. So that's problem one. And the other problem with this case, so first one is ordering. And the second problem is this question of disparity. So disparity is a really interesting concept, which is over fields without any real places. It can happen that even and odd summary ranks don't happen with the same frequency. So you might get more even ranks or fewer even, more with even rank or more with odd rank, depending on what elliptic curve you start with. And these sorts of questions, the disparity questions actually, the difference between the behavior of the family and 50-50 depends a lot on which ordering you choose. So these two sort of play into each other. Disparity questions are mostly solved now, thanks to work of Mazur and Rubin, and I think Klagsbrun worked on that, and then more recently Adam Morgan for abelian varieties. But that is one thing we need to deal with number fields. But mostly this generalization works just fine. Next one is to go to abelian varieties. And this is also pretty reasonable to do. The main problem here is already we see, or I erased them, but the technical conditions for elliptic curves were already kind of sizable, and they get much, much worse with abelian varieties. You need to be more specific, or it's less natural at least to write down what these conditions are. So conditions are harder. And in particular, as opposed to the elliptic curve case, you can't expect the conditions to generically be satisfied. For elliptic curves, you could, because if there were no rational two torsion points, we can make our methods work, and that's the generic case for elliptic curves. But for a generic abelian variety, our methods don't work due to Selmer elements that vanish locally. So the first one of these that really was shown to be important was an element constructed by Poonen and Stoll back in 1999. This is the element which sometimes causes the Cassels-Tate pairing to not be an alternating pairing. And it just ruins everything. And most abelian varieties have a non-trivial element of that form. No offense. Okay. So now generalizing to abelian varieties suggests that we can deal with dimensions of torsion other than 2. So with elliptic curves, we had a Galois module for torsion, which was 2-dimensional. But then this one, it's going to be 2G dimensional, where G is the dimension of the abelian variety. And so the question now is, maybe we can do this for Selmer groups, not corresponding to abelian varieties at all. And my favorite example of this is a Selmer group which gives you what the class group is for a quadratic imaginary field. So here's the example. Take D of fundamental discriminant of an imaginary quadratic field. And take M twisted by D to be just the module Q2 over Z2, but twisted by the quadratic character associated to Q root D over Q. Then what we find is if we take a look at the 2 infinity part of the class group of Q root D, first of all, it has a really boring part that we throw away, which is the 2 torsion. So to do that, we put a 2 in front. But then this group is isomorphic to the kernel of the map taking H1 of M twisted by D. And then we have a bunch of local conditions. So first, the local conditions at P dividing the discriminant are just that the cocycle should vanish. And then at all other places, it's just that the cocycle should be unramified. Oh, excuse me. So I'm going to use I to denote inertia in this case. Okay. So this is a Selmer group which is not associated to an abelian variety, which makes sense. This abelian variety would be half-dimensional. But it's still useful, or we still have the formalism of Selmer groups to deal with it. And specifically, Flock actually constructed a Cassels-Tate pairing that works just fine in this case. That Cassels-Tate pairing is not antisymmetric. And for this reason, we don't get alternating statistics. But we do get all of the ranks of these, the 2, 4, 8, 16 Selmer ranks of this Selmer group. And they're distributed, again, using a Markov process, but one for all matrices as opposed to alternating matrices over F2. OK. Great. And finally, we have probably the most popular sort of generalization, which is, what about P to the k-Selmer? And so in order to explain how we can do this generalization when it's possible, we need to really understand why 2 is such a good prime for quadratic twists. So that's the next section. Okay. And so the reason is very, very simple. I'm going to star this. If we take a look at the 2 torsion of the congruent number curve, but this works for any elliptic curve, and we then twist that elliptic curve, we get something that's isomorphic to it as a GQ module. And for the congruent number curve, this is just equal to z over 2z squared as a module. And the reason for this is on the level of 2 torsion, +1 and -1 are the same. So when we twist by a quadratic character, we're modifying elements by either plus or -1, and that doesn't do anything. But only at 2. This is something that makes 2 special and nothing else special. So yes, this is the basis for everything that follows. And similarly, with this brand new example, we have the same thing. So if we take a look at M, say if we just take a look at Q2 over Z2, and we look at its 2 torsion, then it's just isomorphic to MD 2 torsion. And in this case, it's Z over 2Z. And so in particular, because of this, let me just write this for elliptic curve now. We get a canonical map between the first cohomology group with values in 2 torsion of E, and the same thing for E twisted by D. And the reason this is useful is now we have an ambient space in which the Selmer group lives for both of these twists. And so figuring out the statistics of Selmer groups just amounts to being very careful with local conditions. And so, yeah, I can fit this here. The proposition is take a D equal to P1 times up through PS. So a product of S distinct primes. Then the 2 Selmer group of E twisted by D and the 4 class group of Q root negative D are determined from the first piece of info is just what the PI are mod 8. This gives the local behavior of what the various cocycles in this group are at 2 and infinity. So PI mod 8. And then we need to figure out the local conditions of some primes at other primes. And these are all governed by Legendre symbols. So here I and j are less than or equal to s. Okay. And so again, the reason we have such an explicit description of what's happening here is because we have this correspondent or this isomorphism between the spaces in which these 2 Selmer groups live. Okay. And so now I'm going to go back to the question which I wrote next to 4, which is, how does this generalize? And so the point to make is it can be generalized to other primes, but we always need some version of the starred equation for my methods to work on top of. So let me just give one other example. So we've started with one stacky curve the one of J invariant 1728. Let's go to the other one of J invariant 0. So I'm going to denote this by CEB for cubic because of the Diophantine something something. And I'm going to use this notation to denote the cubic twist of it, which is just going to be y squared equals x cubed. And here we have a d squared. If this was a quadratic twist, this would be d to the d cubed. OK. And so the reason that this elliptic curve has cubic twists at all is because it has Cm by q root negative 3. And in particular, it has Cm by the whole order associated to that field, or the whole ring of integers associated to that field, including the third root of unity. So mu3, we have that set of third roots of unity acts on the automorphisms of ECB. And let's just call a generator of this group zeta. So we have this automorphism zeta of y squared equals x cubed minus 1. And by twisting by this set of using this set of automorphisms, we get a whole bunch of other curves, E backwards superscript D. OK. And so in this case, what we see is, if we take a look at the twist for d equals 1, and we take a look at its 2 torsion, this is not going to equal the 2 torsion for any other twist. So in this case, d is not a cube. But we do have that if we take a look at the set of points which are killed by the endomorphism of zeta minus 1, this is actually preserved as a Galois module going to twists. And so from this equality, we can set up a base case of zeta minus 1 Selmer groups. And then using that as the basis, we can figure out what's going on for the 3 to the k-Selmer groups in this entire family. And that works basically whenever you have a twist. So p order twists correspond to p to the k-Selmer groups. That's where my method works. I will say that the only case where this has been written up fully is in work of Koymans and Pagano, who use this sort of method to deal with p-cyclic extensions of Q and figuring out the p to the k class group statistics in that family. OK. Great. So with my remaining time, let me just explain a little bit of how we make the step from the 2 Selmer group, where everything is sort of, or everything was pretty well understood even in like 1993, to the 4 Selmer group, where we're seeing really new things happening. And so the first thing I want to draw is a little cartoon which explains how we make do without using that start equation. So again, the start equation only works with 2. So it doesn't work for any higher n. But we come the closest to that equation working at 4. Because at least for 4, we can draw an exact sequence like this. And we have another exact sequence which goes through the 4 torsion of E twisted by D. So these are not isomorphic GQ modules, but they're both extensions of the 2 torsion of E by the 2 torsion of E. And so we expect that there's some sort of similar structure here that maybe we can take advantage of. And so in this case, it turns out that there's actually a little bit of classical theory to work off, at least for 8 class groups, which by this example should sort of correspond to something about 4 Selmer groups. So here's a proposition, which is it starts out with work of Rede for the 8 class side. I proved it for the 4 Selmer groups. So for any d greater than 0, sorry. Yeah. There are fields, let me say, Galois extensions LD and LD prime over Q, so that for P not dividing 2D, we have that the 4 Selmer group, the 4 Selmer group of E twisted by D and P, so D times P, I should say, is determined from the class in this field extension LD over Q of P, and similarly, oh my gosh, the A class group of Q root negative D P, it's A torsion, same thing, but here for LD prime over Q P. Okay. And so this is useful for statistics, and in particular, an early result of mine was that just this result plus effective form of Chebytarov density theorem that relied on GRH was enough to prove the first, to prove 4 Selmer statistics have the distribution I gave at the beginning. Okay, so let me close out with just a few words about these fields LD and LD prime. So one thing to note about them is they are non-abelian fields over Q. And in particular, they turn out to be central extensions of abelian fields. So I believe that's called nilpotency degree 2. I'm always a little hazy on that particular terminology. The other thing to note is both of these fields are huge, and they are very different looking, other than the one thing I just told you, that they both have nilpotency degree 2. So the next step would be to come up with similar fields that work for 8 Selmer, 16 Selmer, etc. But that turns out to fail. Or that hasn't been proved conclusively, but evidence suggests that no such fields can be constructed. But what can be constructed are relative governing fields. So these governing fields determine the 4 Selmer group of one single twist. And for that reason, they're really big fields, and they're very different from the Selmer side to the class side. But if we just get enough information to compare 4 twists around a square, we can do that using A, the same field for this, for the Selmer side and the class group side, and B, using a field that's small enough that we can just apply regular Chebytarov to it. We don't need GRH. And it turns out that that particular field generalizes. So those relative fields are based on 2 pairs of primes at the level of 4 Selmer groups, but then at the level of 8 Selmer, they're based on 3 pairs of primes, 16, 4, et cetera, et cetera, et cetera. And with that, the fields you get are more complicated. So this is nilpotency degree 2. The fields of the next case are nilpotency degree 3, et cetera, et cetera, et cetera. So there's something sort of pleasingly Chebuti about this whole thing. But I think that's mostly cosmetic. Anyhow, yeah, that's all I wanted to say. So thank you.
Okay, are there questions?
Okay, so you have these technical conditions on your elliptic curve. Are they necessary in the sense that the statement is wrong when they are not satisfied, or is it just that you cannot prove things when they are not satisfied?
Okay, so that's a really great question. We can prove things at the level of two Selmer groups, and we get different distributions. Yeah, so for example, in the case of partial two torsion, if we don't have a difference between those two fields, the isogeny part is always going to contribute something. And so that changes, that changes the distribution of two Selmer rings. But then at the higher levels, I don't know how to deal with that because all of this relativization stuff really relies on having very firm control on what the Selmer elements look like. And that relies in turn on having Selmer elements that don't look weird. And the Selmer elements of curves of that form look weird. I would really like to get rid of the technical conditions, but that actually looks even harder than, say, expanding to all P or all abelian varieties, etc.
Okay, other questions?
So you can't rule out the possibility that 0% of natural numbers are congruent numbers, or?
Sorry, what was that?
So you cannot rule out the possibility that 100% of the curves have rank 0.
I can, but that's because of work I did not talk about.
Okay.
So back in 2016, how I got interested in the congruent number problem was there's a result due to Tian, Yuan, and Zhang, which gives an elementary condition for D to be a congruent number based on its prime divisors. And this is a really complicated argument in gross Zagier stuff. And then I came in as sort of an eager undergraduate, and I did all the necessary combinatorics to prove that this condition was satisfied 55% of the time. So we know at the very least that 28% or so of D are congruent numbers.
Okay, other questions? No? Okay, well, thank you again.